Hey y'all, I'm Betty DuBois. Since 1997, I've been helping people solve their network and application mysteries by capturing and interpreting packets. Today we're going to spend the next 30 minutes learning what's inside DNS packets. Let's dive in. I have the file loaded here in CloudShark. Think of it as Wireshark in a browser. This way we can all look at the same file with the same version, colors, and filters. Our first file is DNS example coreIT.pcap, and all I did to get this trace file is I went to the coreIT webpage and let it load. Then I did a filter for DNS that matches EngageZ and went ahead and filtered for all of those DNS packets, as well as the HTTP and HTTPS packets that went with them based on the IP addresses in the answers. My goal is to go ahead and show a DNS packet that works the first time, and then we can go ahead and look at them they don't work. Packet number 1 here. Let me scroll over a little bit. There we go. And we've got a nice standard query for EngageZ.net. And then right after that, we've got a nice little DNS response. Let's go ahead and talk about what was necessary for that all to happen. Go over here into the detail and expand the DNS header. The first field is the transaction ID, and what that is for is to correlate the command and the reply. Now, often everyone thinks that there's only one command and only one reply. And when the world is perfect, sure, that's all you'll see. But in reality, a lot of times you'll see a lot more. So imagine for a moment, I sent my DNS query to my server, and, these things happen. The internet ate it. So he doesn't reply because he never even got it. I'm just sitting there spinning my wheels, tapping my toe there, waiting for a response. What's going to happen is I'm going to retransmit it. Now, DNS runs on top of UDP. In fact, you can see the UDP header right there. People think, well, DNS doesn't retransmit. Well, yeah, actually it does in UDP. But it's not UDP that does it. It's actually DNS who does it. So if I have that transaction ID open and I don't get a response, I'm like a little kid. I'm going to send the DNS query again. Let's pretend that makes it to the server. Server goes ahead and replies. Everything's super awesome. Those transaction IDs will all match for all 3 packets. My first request, my second request, and then my reply. Now, let's pretend that I have a secondary DNS server. Well, I'm a very impatient person. And so if my primary doesn't answer me, boom, I'm going to go ahead and ask my secondary because, I'm busy. Okay. But the transaction ID for both of those requests are going to be the same because it's still one query. Now, let's say I send my query to the DNS server. He gets it, but then the reply gets eaten by the internet. These things happen, right? So what do? I'm a 4-year-old. I go ahead and I send it again, right? Well, same transaction ID, right? And the DNS servers, I already answered this, but, she seems nice. I'll go ahead and answer again. Okay. And so he'll go ahead and answer again. If I ask him 15 times for the same thing, he'll answer me 15 times. All right. DNS is stateless. It doesn't keep track of that. But it does use that transaction ID to correlate which command and which reply go together. Right? And that's what its purpose is. Even if we start talking to other servers, which mean other sockets or other flows or other conversations, or for the rest of this 30 minutes, streams, because that's what Wireshark called it. So those might be other streams, but it's still the same transaction ID. Okay? Until I get an answer or I give up. Okay. Now, my next field is going to, whoops, wrong header. Let me close up that UDP header. Okay, that's just going to do that to me again. All right, so transaction ID. Let me go ahead and pop open the flags field. And so the first thing is you should know about DNS is the command and the reply look alike. It's just the replies filled in. So sometimes we'll see fields where we're, shouldn't that go with a reply or something, And that's why. Therefore, we've got to have a field that says this is a command or this is the reply. This is coming from the client. This is coming from the server. And that is this one right here. If I get a 0 there, it's a query. If I've got a 1, it's a reply. That's going to be good for filters. And then the opcode says that this is a standard query The next one is that the message could be truncated. Now, a truncated message, what that means is there's so much data in the packet, well, in the request or reply, that it won't fit in a packet. I've never seen a query too big for that. I suppose there could be, but I've never seen one in 22 years. But in the reply, you will see them, okay? And the reason that you might see a truncated reply is, let's imagine here, I'm going to pause while I move over to my whiteboard. So now I'm over at my whiteboard, and let's say that we've got a nice little query. There we go. That takes up at least 2.5, almost 3 packets, let's say. And just need there we go. So let's pretend I've got, the first packet, right, in the query, and then the second packet, right, and then packet number 3 is leftovers, right? So we got packet 1, 2, and 3, okay? And so let's say the server wants to send that as the reply. Well, we have a little quandary here, okay? Because remember DNS for client queries, it runs on top of UDP. If this was like a zone transfer where DNS servers are updating information about their zone, that's going TCP. That's important. But client commands, not as important. The goal here is speed. Because remember, I have the attention span of a 4-year-old. So I want it now, and I want it now, and excuse me, I want it now. We're going to run it on UDP, right? Which is great until we hit this little situation. So I've got these 3 packets, and it's going to be the reply, and we're kind of stuck because imagine for a moment that when you get it, right, you get it in 2, 3, 1 order, right? Now your DNS database is corrupt, okay, because it's not going to end up like a perfect boundary or anything. So now what do? Can't be running around corrupting databases. Database people freak out over that. What they'll do is they'll go ahead, is the server, server will go ahead and he'll send the first packet and he'll say that it's going to be truncated. It's going to say, hey, it's truncated. Now, so he only sends the first packet. It is the client's responsibility to go ahead, send a new DNS query to the server via TCP. Then what will happen is we'll do this over TCP. And if you get it out of order, TCP will take care of that. There will be sequence numbers. TCP will go ahead and reorder anybody who needs to. Right? That's TCP's job. So that works perfect if it works. So imagine for a moment, I send a TCP handshake request to destination port 53 to my DNS server. Now, quote unquote, my DNS server happens to be Google's public DNS, which is like everybody's, DNS server. And I send a TCP request, handshake request to him. Okay, the firewalls in front of him are going to go, no, that's not going to make it. If the data that I need, the most that I need is what's in the first packet, then great. If I need all 3, I'm in a quandary. That's one of the things that, can be a challenge. Let me come on back. Here we go. But remember, the requests aren't truncated, but the responses might be, and that's something to watch for. I told the server that I want him to do recursion. What that means is, Google, sweetie, if you don't have the IP address for the name that I want, could you go find it for me? That's recursion. So let's check out how that works. I'm going to pop up here to my whiteboard. So this is me. I need that IP address and the Google public resolver. All right, he's got to go through some steps. If, it's in his cache, then he's just going to reply. Boom, done. If not, then what he's going to have to check is if the authoritative resource for engagez.net, if that authoritative server, does he have that IP address in his cache? Awesome. If he does, what we'll do is we'll just go ahead and we'll query the authoritative name server. That server will go ahead and say, oh yeah, I got that on over at 104.18.55.77. It's fabulous. Go there. Okay. And that works perfect. What if I don't have that in my cache? Well, then what we got to do, we did a query for engagez.net. So .net's our top level domain, or TLD. My server's going to go ahead and check his cache. Do I have an IP address for a top level domain server for .net? Well, if he does, awesome. All right. Then he'll go ahead and send a query to the TLD server and say, hey, can you guys tell me anything about engagez.net? And then the TLD server will go ahead and say, yeah, we know them. Their authoritative DNS server is 173.245.58.69. Then our DNS server would go ahead, put that in his cache, right? Because he'll need that, later. Somebody else is going to want it. He'll go ahead and ask, hey, I need an IP address. What IP address should I use to go ahead for engagez.net? Because he's going to have a TLD in his cache. If he's been up and running longer than like 3 minutes, he's going to have one, but for a top level domain. But let's pretend that he just booted up. Well, then what he's going to have to do is he's going to have to query a root server for top-level domain.net. And so he'll be hard-coded with that. So when he boots up, he already knows those addresses. And there's 13 for A records, which would be your IP4, and then there's another 13 for your quad A's, which is IP6. And if he has to go there, then what's going to happen, he's going to do the same thing. He's going to say, hey, I need a TLD. He's going to have that in his cache. Okay, seriously. But then he'll go to the root server, say, hey, I need a top-level domain for .net, give me an IP, and then the server will go ahead and give him the IP for the TLD. Then he'll go to the TLD and then get an IP address for the authoritative name server. I'm tapping my toe right now, waiting for the answer that I need. Goes to the authoritative server for engagez.net, and then finally, dun, 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 he can tell me the IP address. Oh, meanwhile, every single thing every piece of answer, he'll go ahead and put to his cache in case for the next person to answer, right? But then what he sends to me is, boom, here's your IP address. And that one little bit is that whole slide, alrighty? Then I got a bit that's reserved, and then I told the server that non-authenticated data is completely unacceptable because I want you to go to the authority every single time. And the Google server will just laugh and laugh and answer from cache, okay, which is what he should be doing, all right? Remember, clients are like children, all right? If they just because they ask for stuff, doesn't mean they're going to get it, right? But that's what I'm asking for here. I'm asking him to go to the authoritative server every single time, which would be silly. All right, then I have my question, and I don't have any authoritative resource records. I have no answers, no authorities, no additional resource records because it's the query, okay? And if I expand my query, there we go. So if I expand my query, then I can see that for engage.net, that's 11 bytes long, right? And 2 labels. So the word engagez, 1 label, the word net, 1 label, all right? And then the type is an A record. So I'm interested in any IP4 query, IP4 addresses, right? So a class A record IP4. And then CloudShark goes ahead and tells me, hey, the response is in packet 2. And a little secret about CloudShark, they go ahead and use all of the dissectors from Wireshark, all right? So it's just like looking in Wireshark, only a different visual, all right? But all of your dissectors, which are your decodes, like this field, there we go. So that field highlighted in hex, that's the DNS name, DNS query name. And so just like it is in Wireshark, okay? There we go. And the cool part is it's a link in Wireshark to go ahead and go to that response because here it's in packet 2, but in real life, it is never in the next packet, okay? So if I go ahead and I click on that, here we go. And then if I come down here, I can see what packet the response is in. Okay, now, so I come over to packet number 2. Here we go. Notice the transaction ID matches. And if we go ahead and look at the flags, we can see the message is a response. This server is not the authority for the domain, right? So if maybe you were at the office and you were capturing some packets and you talked to your authoritative server, then that bit would be flipped. All right. Server says, okay, so, it all fit in a single packet. And trust me, truncated happens, but it's not common. And the client asked for recursion, server's capable of doing recursion. And you wanted it to be authenticated data. You're lucky you're going to get what you get. And then in the reply code, that's what I need. The reply code says, hey, did this work or not, right? So all zeros means yes, this is a good reply. There's no issues, no errors, right? And it's 4 bits. So 4 bits of zeros. So that means if there's a 1 in any position or multiple positions, then that means it's not going to work. It's not a good response or some kind of error response. And so that's going to be a great filter for us to use in just a minute. Okay. I asked a single question. I got 2 responses though, because it was a beauty day. All right. And but I didn't get any authority resource records or additional resource records. So the query is repeated. Oops, expand that. There we go. And then in the answers, here, let me get the answers open. Get all that open. There we go. And then scroll down. There we go. That looks better. So in the answers, I have already, you asked for engagez.net, and you get to go ahead and cache this information for 299 seconds. All right. And the IP address is 104.18.55.77. Now, I have no idea what that number started at, but 300 seconds is the default, which is 5 minutes. If, let's guess, because, we don't know, let's guess, though, that 299 started at 300. So the Google server, has had it for a second, and then he replied to me. Coming on down. My IP address, 104.18.55.77. And then I have another one, 104.18.54.77. I'm going to take the first one on the list and run with it. In fact, so the first one is 5577, right? And I'm going to go to the next SYN packet. And sure enough, in the IP header, it is 104.18.55.77. Okay, so I took the first one on the list, right? And then started talking to him. And I am always going to do that. I've seen maybe like 0.5% of the time it uses something besides the first, so I've only seen like a couple in my whole career. So I can't say never, but predominantly, normally, what you're going to see, first one wins. Okay. Now, the reason the server gives multiple answers is to do what they call poor man's load balancing. Now, I don't know what the subnet mask is, but let's pretend, that's a class A number. So let's pretend they're using a B mask. Then these 2 addresses are in the same location. And then it's trying to do load balancing. And it's going under the assumption that DNS servers along the path, when they receive one of these packets and they, had to do a query for one of their clients and they put it into their cache, every time they reply back to their clients, they go ahead and give it to their clients in different order. So like I would take those 2 addresses and I like flip them back and forth, right? And that's what they call round robin DNS, which is a great idea, assuming that all DNS servers do that, which guess what? They don't. Sometimes it works. Okay. Now, if they're depending on the subnet mask, these could be in 2 totally different locations, then it is for fault tolerance. I'm going to get to, which is a great thought. But if I got 2 IP addresses and they both have the same time to live, which these do, and for your specific record types, types of queries, you're going to have the same time to live for each query type or record type for all the records in the database for your zone. If I'm going to do fault tolerance, then I have these 2 IP addresses in my cache, right? But they both have the same time to live. It would be super awesome if, hey, let's say I send a SYN to 55.77 and, he's having a rough day, right? And he doesn't reply and I try again and again and he doesn't reply. So I give up, right? And then I just right next go to 54.77. That would be so awesome. I don't do that. All right. None of your standard operating systems are going to do that. And so what happens is you got to wait for a timeout, right? And so your operating system might wait for your cache to time out, or it might time out earlier than that. But you're going to do a new DNS query. You're not going to go to that next IP address. So great thought, Maybe in the beginning that's how it worked, but that's not how it works now. And so the moral of the story is the fault tolerance piece isn't working. And if you want to go ahead and do load balancing, then use a load balancer. Don't depend on round robin DNS. Okay, you can't depend on it. Wireshark and CloudShark, go ahead and calculate how long did it take. I'm capturing at the client machine. So how long did it take for the client to send that packet out, go out through the internet, hit the cloud, go, who knows where, hit a server, come on back, right? How long did that take? So I've got 20 milliseconds. Some of that is just, network round trip time. Like if I'd pinged 8.8.8.8, and then some of that is DNS time. Let's just go ahead and try. How long does it take to get to 8.8.8? So pop open a command line here and we'll ping 8.8.8.8. There we go. And poof. Yeah, we're pretty much looking at about, 106. Ouch. 24 to 106 milliseconds. I got to get all the way out of Comcast. I got to make it to Google. It's got to go ahead and make it back. And so my guess would be 19 of that was network delay at that day. And then 1 was DNS. Okay. But that's just a baseline that you should consider. Let's see what it would look like if I had some error messages. So this is a nice standard, beautiful command and reply. There's actually a number of DNS requests. In fact, I'm going to go ahead and do a filter. There you are, filters. Filters, there we go. And I've got some filters in here for you, okay, that you can go ahead and use while you're looking at this here in CloudShark. And but I'm just going to do one for DNS right quick. There we go. And I've got a number of DNS requests within the trace where, we had to go ahead and do a DNS query, and then we had to go ahead and do another DNS query to get information for our OCSP to check on the validity of the certificate for EngageZ. Okay, and that's why you've got extra. And then I've got a server H, EngageZ.net, and the answers for that one. Now, that one's actually quite a nice one because it has a canonical name. All right, it's actually an alias. Either A, drop down in your filters and choose DNS, or just come on down to packet 396. Be faster to filter, but I'm just saying. And in the response for this one is for H, EngageZ.net. I have what is known as a C record. Here, let me scroll down just a little bit. There we go. So I had asked for H, EngageZ.net. And then in the responses, it came back saying, and here, let me move this over. Here we go. It came back saying, actually, that's an alias. The real name is dualstack.alb.app. A whole bunch of numbers, US, East, L, ELB, load balancer, Amazon, AWS.com. Yeah, that rolled off the tongue. And then the DNS server says, all right, and here are the IP addresses for that really long name. And so I've got a 3.217.29.180. And then CloudShark goes ahead and puts in the name just to make it a little easier for you to read. Quite frankly, I think the IP address is easier. And then we have another IP address for that same canonical name. And so oftentimes, it's easier for us humans, like let's pretend I'm the developer of the page. And it's easier for me to go ahead and put in references to an h.engagez.net server because, that's where I work and I know all those servers, they're super awesome. But for reality purposes, EngageZ is not actually hosting some parts of the platform. And so those are offload, they've got those on an Amazon web server. And so the Amazon web server naming convention is what's really has to be used. And that's why you'll have aliases. It used to be we all had our own web servers, right? It was great. But then you want to do scaling, right? We want to scale to like millions of people. Well, that's not going to happen on one server. So we've got to go ahead and then expand multiple servers. And then we've got to go ahead and extend it out to people who do nothing but host for a living, right? And do it well. And so that's what you'll see when you see those canonical names. I have another link for you in CloudShark, and in that one, we have a whole bunch of error messages. So there's examples of silence, we just don't reply. How does this client react? We have examples of slow response, we have examples of retransmissions, we have examples of DNS error messages, just to go ahead and give you an idea of what some of those things might look at. But I've used up all my time, so I hope you enjoyed having a chance to go inside the DNS packets, and be sure to look at the description below and check out some more resources. I'm Betty DuBois. Thanks for coming to Bettyland.